Hello guys, in this video I am going to solve this particular question from book Engineering Circuit Analysis by Hayt Kemmerly and it is a question from chapter 7, question number 15. So the question says that for the circuit shown in figure 7.45a, calculate the voltage labeled VC. So over here I just need to determine VC. Now we know that for a capacitor, since the current is given as C dV by dt, right? So it means that current will be there through the capacitor only if voltage is changing. If voltage is not changing, then it means that the current through the capacitor it will be zero. It means that, like, if let me write, if V is changing, then I is not equal to 0. It means there must be some current. Whereas if V is not changing, means it is constant. In that case, I will surely be 0 as per this particular equation, right? So now considering this point, like if I is equal to 0, it means that voltage across the, if I is equals to 0, it means that the element is open circuit, that it is a open circuit, right? It is a open circuit. Why? Because we know that if the circuit is open, then only there will be no current, then only current will be 0. So overall, with all this, what we can conclude, that this capacitor, because over here the voltage, the current that is supplied to the circuit, it is constant, right? And since it is constant, so a constant current must be flowing through all the elements of the circuit. So since it is constant, so it means voltage across all the capacitor and the resistor will be constant, and hence this capacitor, the current through this capacitor, it will be 0, right? And if the current through the capacitor is 0, so it simply means that we can replace the capacitor with open circuit, right? So I can, if I redraw this circuit, the circuit will then look something like this, right? This is 13 ohm, this is 10 ohm, this is 7 ohm, this is 5 ohm, and this is our VC. Remember that I will be 0, but I equal to 0 does not mean that voltage will be 0. There may be some voltage, right? So there may be not equal to, because it may also be 0, right? It may or may not be 0. But if I is 0, then our VC can be 0 or non-zero. So both are possible. So overall, like with this reasoning, simply what we get, we are able to redraw this circuit where we do not have the capacitor. And once we get this circuit, now we can solve this particular circuit using any theorem, using any rules, and to determine the value of VC, right? Now for this particular circuit, if I just consider, because this part is open, right? So overall I just have this part of the circuit. So let me redraw it again. So my circuit, it is simply this, right? 13 ohm, this is 7 ohm, this is 10 ohm, and this is 4.5 nanoamperes, right? So now if and this part, since this part is open from here, So as such, no current will flow through this branch, so I can remove it. Now if I apply the nodal analysis considering this as a node and this B as the reference node, means VB is equals to 0. So writing the nodal analysis equation, I can write like considering this as a current, so the equation will be VA upon 10 plus 7. Then for this it is VA upon 13, and for this it will be, because the current direction is different, like over here I assume this, so it will be minus of 4.5 into 10 power minus 9, right? 10 power minus 9 equal to 0. So this is our nodal equation, and now solving this equation I will get like it will be VA 1 upon 17 plus 1 upon 13 equals to 4.5 into 10 power minus 9. So taking the LCM, I will get 13 plus 17 upon 13 into 17 equals to 4.5 into 10 power minus 9, right? So it will be like 13 and 17, it will get added up, so VA will be equals to 30 upon 13 into 17 into 4.5 into 10 power minus 9, right? So I will get VA equals to 33.15 volt, right? It will be, let me recalculate it using the calculator. So it is let me do it, 4.5 into 13 into 17 divided by 30. Yes, it is, answer is correct. It is 33.15 nanovolt, nano because of this, right? Once I get VA, so this is my VA. So from this I can determine this current, let it be I, right? So I will be VA upon 10 plus 7 equals to VA upon 17. Now VA upon 17, and substituting the value we will get 33 point, it is 33 point, VA is 33.15 nanovolt upon 17, right? So it will be like 13.5, we will get current as this, right? Now if I get I as this, so from this I can determine the voltage across this, let it be V7. So what will be V7? V7 will be I into 7. So our V7, it will be I into 7. So if the voltage, like coming to this circuit, if the voltage across this, it is V7 across 5 ohm, since no current was flowing, so this V5 it will be 0. So our V7, it is I into 7, it means it is substituting the value of I, we get it is 33.15 upon 17 into 7 nanovolt, right? V5, it is equal to 0 because no current is flowing through this resistor. Now calculating VC. VC will be, because plus terminal, this plus terminal it is towards 5 ohm. So we will write V5 minus V7 because minus V7 because minus terminal is towards 7 ohm. Now substituting the value in this equation, simply what we will get? We will get 0 minus V7 is this. So the answer, like if I solve this, so this will be 13.65, right? 13.65 nanovolt. So substituting this value, I will get 13.65. So it is 13 minus 13.65 nanovolt. So this is the answer to this question, where we need to determine the value of VC. So our VC is minus 13.65 volt. Okay, nanovolt. It is nanovolt. So this is the first part of the question, where we just need to determine VC for this particular circuit. Now in the second part of the question, it says that our circuit is this. Now applying the same reasoning means, now over here we need to determine the voltage across this capacitor. And now again, because the current source is constant, so again what we are going to, redraw the circuit where we just remove this capacitor. So our circuit, it will be so we need to determine this VC, right? Somehow. So how we can determine? Again, we can apply the nodal equation, right? How? If considering this as a node, right? Considering this as a node, or we can do another thing, because over here I need to determine VC. And what is VC? VC is either the voltage drop across this, since this VC, it is parallel to the current source, so VC will be the voltage drop across this current source, or it is the voltage drop across this resistive circuit, right? To combined resistive circuit. So what I can do, instead of going for a nodal analysis, I can reduce the circuit by taking the equivalent resistance. So calculating the equivalent resistance, this 13 and 5, it can be combined. And if I combine this 13 and 5, what I will get? I will get 18. So my circuit, it will be like this. Right? It is 10, it is 7, and it is 18 ohm by combining this 13 plus 5 equals to 18. Right? Now after this, I can combine these two. So if I combine these two, what I will get? The combination of these two resistors, it will be 7 into 18 upon 7 plus 18. So it is 7 into 18 upon 25, right? Upon 25. And now if I can reduce this circuit to this, right? And now since these two are in series, so I can combine them, and the combination, it will be 10 plus 7 into 18 upon 25, right? And if I solve this, I will get it. The answer is 376 upon 25 ohm, right? So by circuit now, by circuit it will be and we have a current source. The value is 376 upon 25 ohm. This is our VC that we want to determine, and this is our current source, which is 4.5 nano ampere, right? Nano ampere. This is our VC. So you can see now our reduced circuit is this, and from here easily, because this is open circuit, right? So our what is our VC? VC is equals to the voltage drop across this resistance. Let it be V1. So since the current that is flowing through this resistor, it is current flowing is 4.5 nano ampere, right? So directly we can determine V1. V1 will be I into R, which is I is 4.5 into 10 power minus 9, and into resistor R is 376 upon 25. So the answer, if you calculate, you will get the answer as this. So this is our VC. This is our VC. So simply to solve this type of questions, simply what you need to do, you need to check that if the capacitor is connected to a constant source, right? It may be the voltage source, it may be the current source. So if it is connected to the constant source, and if it is connected from from longer time, right? Like over here in this question, it is not mentioned that if it is connected, if the capacitor is connected to this constant source just right now, or it is connected from a long time. So it is not mentioned anything. So since it is not like nothing is mentioned, so over here we are going to consider that the circuit is in this situation from the last long time, and considering that, we will consider that the current through the circuit, it is stabilized. And if it is stabilized, it means that there will not be any current through the capacitor, because our source is constant, right? So simply you need to replace the capacitor with the open circuit. So with this, I end this video. If you have any doubt, you can put it in a comment box. Do subscribe my channel and share this video with your friends and colleagues. Thank you.